Okay, so let's get going. So today I'm going to wrap up a little bit of Wednesday's lecture and then sort of focus on homework 4, which I think we have released, or you're just going to do it today?
It's up.
So it's up. Okay, so you can have a look. So like I explained, previously, so the homework 3 is due on Wednesday next week, but then in 2 weeks we have to get started with the final project. So the idea is that you should try to complete homework 4 in the next 2 weeks. Okay, so we sort of push the due date to give you a little bit more flexibility, but at the end of the day, the work needs to be done by the end of the quarter. So essentially, you have a little bit of freedom to move things around, but there is definitely some amount of work to be done, and so make sure you organize yourself around that. So homework 4 is more. Is probably one of the more complicated homework for this, at least for the CUDA part, definitely. And so you probably want 2 weeks for that. And then again, Friday in 2 weeks we're starting the final project. So I strongly advise to complete homework 4 before then. Although in terms of the deadline, the due date for homework 4 is actually past that. But I'd recommend sort of finishing early on homework 4. So you can focus on the final project, which will be final project is definitely significantly more involved, and for the final project you'll have starting 2 weeks from now till the end of the quarter to complete. So so the first sort of comment is sort of a more general philosophical comment. And I'm not going to go too much into the details of that, but it's sort of a general concept that you should have in mind when thinking about processors, network communication, and generally speaking, operations on a computer. So I'm going to take this example, but it's actually quite. It's actually a very good example, although it seems completely unrelated to computing. So basically, the idea is so you're trying to produce these some goods, and it's commercially beneficial to outsource the fabrication, and so you have some plant in some other country where your goods are produced. So I'm just taking this example, but obviously China-US trade, but just an example will do here. But the point is, how does this work? Okay, how is it possible that it's economically viable to do that? Okay, pencils are very cheap. You have to cross halfway across the world, but still, it's commercial advantages. So the idea is, well, okay, so the labor is cheaper over there, but then you're going to use a very slow means of transportation. Basically, some cargo ship and so on. So gigantic ships, but definitely take a couple of months to cross the Pacific. So the reason why this works is that so the operation itself takes a lot of time, but if you set things up correctly, you can actually sort of mass produce pencils, okay, and mass sell them. And so the idea is as follows, okay. If you have a process in which, for example, you only have a single ship, then this is going to be very difficult. Let's say it takes 3 months to cross. So obviously, in a cargo you may have a lot of pencils, but there's a limit to that, and there's going to be huge delays between shipments. Okay, between the ordering and shipping and so on. So very, very long delays. Okay, and so the fundamental problem here is that it just takes so much time to cross the Pacific. But curiously, if you go into parallel computing, okay, and you use multiple ships instead of just one ship, you can actually completely change the picture and go from this very slow process where a ship arrives, let's say, every 3 months, to a ship arriving every day. Okay, and it looks all of a sudden that, you know, a new ship arrives every day, so, you know, it takes 1 day to produce pencils. Of course, it's not true, but, you know, it's going to look like this. And the trick is to use many, many ships, okay, and to have, you know, a large number of ships constantly, you know, going back and forth between China and the US. Okay, so this is the idea of parallel computing. Okay, and okay, so if you look at a computer, this is actually exactly what happens. Although you know, you may not sort of realize it. So it looks like, oh, a ship is coming every day or every cycle. There is a floating point operation being done, but it takes way longer than a single cycle to do a floating point operation. So how is it possible that every cycle you can crank out these operations, although it may take, you know, say 20 cycles or 30 cycles to perform the operation? Okay. Well, the idea is that let's say you want to do an addition. The idea is that you have this pipeline. So let me draw it up here. You have this pipeline where instead of viewing this one operation in this manner, okay, that is in just one box. So essentially, you know, you order a ship, you wait, it arrives, you unload, you send it back, and so on. So you just have this sort of monolithic view of the operation. Instead, you're going to break it up into stages, okay, such that, you know, you move data in here, and every cycle, the data moves, you know, through each one of these stages, and then you exit here, okay? Right. And so this is similar to essentially having a ship, you know, start from China right here, and sort of slowly making its way to the US, okay? But you see how, you know, to make this work, you need a lot of concurrent operations. Okay, so for example, in this, you know, in this diagram here, let's see, we have like 8 stages. Okay, and so essentially, if the number of, say, and let's say this is doing addition between 2 floating point operations, floating point numbers. If you have many additions to perform, actually more than 8, you know, it has to be a number large compared to 8. So let's say, you know, or 64 or 100 of these additions. Then you can start with the first addition, okay, and then when the first addition moves to second stage, you go to second addition moves here, third addition, and so on. So of course, initially, you know, nothing happens. You have to wait 8 cycles to see the result of the first operation. But once the first result comes out, then magically it looks like every cycle you're pumping out, you know, additions. So it's basically like these ships that, you know, initially you need to wait for the first ship to arrive. But once the first ship arrives, then there is one immediately behind, and so on, like a day behind. And so every day it looks like, wow, there's a new ship that's coming in. You know, I can get a new load, you know, a new ship of worth of my goods every day, although, you know, China is really so far away. Okay. And so this is an extremely important optimization, right? So when designing hardware, this is an almost sort of systematic idea that you need to do all the time, because basically the cycle is very, very small. Okay, in the cycle, what can you do? Not very much. Okay, you know, you have to go through a bunch of transistors and so on, and just how fast the transistors are changing. So you cannot do a whole lot every cycle. So whenever you have to do, you know, non-trivial operations, so these floating point units, memory access, you know, and so on and so forth, if you just view this as sort of a monolithic block, it doesn't work out. So every time you architect designers, you know, they figure out the architecture and, you know, the transistors and so on, and how to sort of design their processor, every time there's something that is sort of long, they immediately try to break it down into a sequence of steps, okay, that are such that, you know, once the data moves to second stage, then the first stage is available for further processing, okay? And so you have these gigantic pipelines that are built, and so this leads to, you know, two separate concepts. Okay, so this is sort of, you know, this diagram here. So this leads to, you know, two separate concepts. So the latency and the bandwidth. Okay, so the bandwidth is sort of the quantity that is sort of advertised. Okay, so the bandwidth is basically saying, well, when you reach top speed, okay, or essentially when your pipeline is completely full, how quickly is data coming out? Okay, so every cycle you have a new operation, or for example, when you quote memory bandwidth, it's just that's the rate, okay, that you get, like, gigabyte per second, and so on, how fast things are coming out. So that is the bandwidth, and that really essentially depends on you know, your ability to break down your operation into these steps. But say if each stage actually you can break it down so that each stage is just one cycle, then the bandwidth is actually just one cycle. Okay, every cycle, boom, you have something coming out. It's huge. But and then you have this concept of latency. Latency is the actual time it takes to perform the operation, pretty much. Okay, so it's the time basically from start to finish. So latency is defined as, you know, if you just do your operation on a single piece of data, how long is it going to take? That's pretty much that's the latency. Okay. And so you can hide the latency through concurrency. Okay, you can hide the depth of this pipeline. Okay, how deep this this pipeline is, you know, through concurrency. So the idea is you break it down to stages, but then you need a number of parallel independent work that's large compared to the depth of your pipeline. Okay, because as you do these operations, you know, none of these additions, for example, can depend on the result of you know, previous additions. Because obviously, you know, you won't see the result of the first operation until you're done here. So everything else needs to be completely independent. So you need a lot of concurrency. Okay, and so that's basically, you know, so hence, you know, this actually makes it rather difficult to. Okay, this actually makes it rather difficult to write CUDA code for this reason, because what you need to do is, first of all, you need to have an amount of work that's sort of large compared to the number of cores. And, you know, in Volta, it's really a lot of cores. It's in thousands. Okay, so you need a data set that's large compared to that. But in addition, you know, you need even more than that, because you need to fill up these pipelines, essentially. So, for example, if you have some operation, you know, like again, addition or multiplication and so on, it's not enough to just have one for each core. Okay, you need to have multiple of them that are sort of independent that can be pushed through this pipeline. Okay, so you need a gigantic amount of concurrency. Okay, so I'm going to sort of focus a little bit on that in the next couple of slides. So how to maximize concurrency? Right, basically you want to have as many threads as possible, you know, issuing instructions, obviously. So basically each thread would be sort of, you know, pumping, you know, one instruction into this pipeline. So if you have more threads, you know, you have more of that coming in. But the other thing is actually possible. So I'm not going to discuss much about this. But there's also so-called instruction level parallelism, and that's pretty much, you know, kind of very closely related idea. But if you just look at the level of a single thread, okay, if a single thread issues operations that are independent from each other, okay, so, you know, it could be something as simple as x equal a plus b, and then, you know, y equal, you know, well, actually, I don't know if you can probably do a plus c. So you might be able to, probably can be used with registers, but essentially the second instruction, you know, is independent of the result. There's no x in it. Okay, so you can issue essentially these two additions sort of concurrently, or rather, you know, you can pump a plus b in, and then a plus c and so on. And so by issuing more, by giving more concurrent instructions, okay, that can be done independently of each other, then you can just speed up all these pipelines. So it's very common that, for example, when you write CUDA code, you very often have this trade-off between, increasing the number of threads, okay, or having each thread issue more instructions in parallel. Okay, so there is sort of a limit to this instruction level parallelism, but very often you can sort of play around with that and have each thread, for example, issue instructions that are independent of each other and try to create more concurrency in this manner. So instruction level parallelism is something you do by essentially modifying your code and making sure that you're writing your code in a way that you have certain sequences of instructions that are essentially independent of each other and can be done concurrently. But the easiest is just to have more threads in live that can just issue instructions, and you just create a lot of concurrent work, and hopefully the hardware can just optimize that. Okay, this is sort of the easiest, so I'm going to sort of focus on that. So, so what I'm going to focus on is, obviously what limits the number of threads is our hardware resources. Otherwise, you just allocate, 1 million threads, and everything would be good. But so what limits the number of threads you can run are hardware resources, and so this is where things get a little tricky. Because essentially, you want to figure out what is the the dimension that's limiting the number of threads you can run on your processor. What's the limiting, a sort of factor, and is there a way to get around that? Okay, and we'll see that there are tools to do that. So there's the maximum dimension of a grid, but that's typically not very important. Of course, if you have a very small problem and you have very few blocks, okay, then you're going to run in difficulties. But typically, you have a large number of blocks, and so you're fine here. So now critically is the dimension of the blocks, number of threads per block, and there are some limits here, and so we'll talk more about that. And then as you've seen, there is a maximum number of threads per block, and also there's a maximum number of blocks per streaming multiprocessor. So meaning that if the blocks are very, very small, okay, then it seems like, well, we can have just more blocks, but there is a limit to just the number of blocks that can live inside an SM. Okay, so each block should be reasonably large, otherwise you're going to be hitting this this limit here of 16. Okay, there's also a limit on the number of warps, and so these are sort of equivalent number of threads per SM. There's obviously a limit on the number of registers that a block can use, and there's a limit on the shared memory. So for example, if you allocate memory, well, this may limit the number of blocks that can run, because each block needs to require its own chunk of shared memory. So you go from 1 block to 2 blocks, you double shared memory. Okay, registers is more proportional to the number of threads, basically. So each thread needs to have a little bit of register space. So that sort of scales roughly the number of threads. Okay. So how do you how do you make sense of this, and how do you optimize around this? Okay. So essentially, you need a tool which tells you, okay, for a given kernel, how to figure out these parameters, and essentially that means for us the main tuning parameter will be the size of each block, how many threads you want to have in each block, and then the number of blocks that's typically cannot really be controlled, but it will tell us at least how big of a problem you need to reach sort of peak performance on your GPU. Okay, and if the problem is too small, well, maybe there's nothing you can do about it, but at least you know that the GPU is not going to perform well on this problem. Maybe you have to run on the CPU and so on, and find some other route. So so how do you figure out how many threads are going to be running on each streaming multiprocessor, and then you have this concept of occupancy, which is basically let's say you have 2,000 threads maximum on each SM. Well, what fraction of these 2,000 are you going to be able to use? Okay, so occupancy of 100% means that you have 2,000 threads running on each SM. Let's say you have 1,000, then you'd say you had 50% occupancy. So occupancy is basically the fraction of this maximum that is actually running. Okay, so hard to say, what's a good occupancy, but you want to be pretty high, definitely above 50%, maybe 70%, 80%. But again, it also depends on this instruction level parallelism, right? If you have a lot of instructions in your code that sort of are independent of each other, then you can get by with relatively fewer threads or lower occupancy. So, so you have two techniques to kind of go about this problem. One is is okay, but maybe a little complicated, because essentially you can use the CUDA API. So you have to make a call in your program to figure out these parameters. So it's kind of awkward when you write the code, because essentially it means that before running the kernel, you need to run these functions to figure out the right parameters to run the kernel. So it makes it a little bit more complicated to write the code. So I'm just highlighting here a couple of functions. So here you have CUDA occupancy, so it's going to give you, trying to maximize the occupancy, max active blocks per multiprocessor. So essentially, it's going to try to predict, to calculate, for a given block size, the number of blocks that are going to be running on each SM, and then you can optimize, your block size in order to, maximize this number. And then there is another, another function related, which gives you not just a recommended block size, but also tells you something about the grid size, like how many blocks should you have in order to properly use your GPU. Okay, so you have these two CUDA functions you can use, but a tool that's sort of quite useful and hopefully makes more sense is just a spreadsheet that NVIDIA has written, which is called the CUDA Occupancy Calculator. So if you go, you can click on 9 on the slides here, and it will open the spreadsheet. So this is what the spreadsheet looks like. So I'm just going to, just open it up, right here. So let's see, zoom out a little bit, so you can see, what's. So it has, a number of things here. So so you start here on the left. So actually, let me zoom back in so you guys can see what's. So if your computer is open, you can have a look at this. So here, so you essentially need to, look at just step 1 and 2. Okay. Yeah, they say 1, 2, and 3, but it's really just 1 and 2. Everything else below that is you cannot edit. So here you have to enter the compute capability. So we're 3.7. Here, this is more how the card is configured. Okay, like how many shared memory is available. Okay, versus L1. Okay, and then here you have a couple of parameters that are sort of the things that you want to sort of optimize a little bit. Okay, the main one obviously is number of threads per block. Okay, so this is a number you're going to be sort of playing with to figuring out how many threads you want per block. Okay. Next one is registers per block and shared memory per block. So I'm going to talk more about that. Shared memory per block. Can you guys see the slides in the back? Okay. So shared memory per block, basically, this is just the amount of shared memory that you're allocating. So here I took this code, transpose.cu from last lecture, looking at how many shared memory we're allocating, and see this is just the amount of shared memory that we have per byte. Okay. Just zoom a little bit more. You can see this. And here, registers per thread is actually something that the compiler can tell you. Okay, so this is that is not easy to to figure out. You need to essentially, when the code gets compiled, the compiler spends a lot of time optimizing the use of registers, right? To use as few registers as possible. Of course, there are dependencies between all the operations, so that's why it's a complex problem, right? Changing the order of the operations and so on can sometimes save a little bit on registers. But this is done at compile time, right? During execution, there's no really change with that. Everything is sort of set at compile time. And then here you have some data that basically corresponds to what's happening when you run this kernel. So for example, it's going to tell you how many threads are active. So here, it's a 2000. So essentially, with this configuration, I reach 100%. And this is also shown here. This is where I'm at here. And 64 is the maximum number of warps. Okay, so I'm at the maximum here. Okay, so you have 64 warps multiprocessor. Maximum. So you have 16 active threads. So 16 blocks, and then occupancy is 100%. Okay. Then after that, below that, you have some physical limits. So basically, these are all the numbers I was giving you. So you have 32 threads per warp, maximum number of warps, maximum number of blocks, and so on and so forth. So this is the resources, the number of warps, registers, shared memory that you have across essentially on each SM with all your blocks and so on. And here, also some important numbers, which is basically, this is currently the limiting factor. Okay. So here, for example, I picked blocks that are pretty small, 256. So the limit I'm hitting is 16 blocks, right? I have 16 blocks, so we cannot allocate more. Okay. So for example, if you if you look up here, okay, so here you have some help. Here, if you're curious, there's a bunch of numbers basically that are used in the spreadsheet with all the data and so on, but don't really need to look at that. So for example, if you look here, so this is sort of the key plot here, and this one is actually a little tricky to understand. So this is showing, as you vary the number of threads per block, so this is your key parameter, how the occupancy is varying. And so it's very irregular, so that's why this essentially you have the spreadsheet, because it is a non-trivial problem, because depending on how you pick threads per block, you hit different essentially different limits on your hardware, and so you get this sort of weird behavior. So for example, here, if you put few threads per block, essentially the limit is you allocate 16 blocks, but then you cannot go beyond that. So you're limited by the maximum number of blocks that can be allocated. Okay, so this is basically here. That's why it increases just linearly, because basically the number of blocks is fixed at 16. And then just multiply by the number of threads per block, and that's the total number of threads you're going to have. So once you reach 128, you're at the maximum. So what's happening is, so here you're at 100% occupancy. So here, you're at the maximum. If you increase the number of threads per block a little bit, okay, then you have to let go of one block. Otherwise, you have too many threads. So you let go of one block. So this is why you have these white false here. Okay, this basically corresponds to just adding 32. So everything goes by 32, obviously, because that's one warp. So every time you add, one more warp, you reduce and you remove an entire block. That's why it goes down. Okay, you just make each block a tiny bit bigger, but then you remove one block. Okay, and what's happening is initially you have a lot of blocks, 16 blocks. So when you just remove one block, it's not super visible. But as you have fewer and fewer blocks, this effect is more and more pronounced. So this dip here becomes more and more pronounced. Okay, so you can look at this plot, exactly what's happening. So initially it's very smooth, but initially you have the number of blocks is going down very slowly, and then at some point you're able to essentially the number of blocks sort of is fixed. So here you just see the increase in number of threads, then you lose one block. Then here number of block is fixed, so it just goes up, lose one block, number of block is fixed, and so on. Okay. So this is the main plot. And then here, if you look to the right, you have other, so this is a little trickier, but this is, for example, if you were changing the amount of shared memory allocated, so for example, if I allocate more shared memory, then progressively, the occupancy would go down because it would just run out of memory. So this is something that perhaps can be changed. Okay, in your code, typically, you can control the amount of shared memory you're allocating. Okay, so you want to allocate as little as possible, but there are many factors, obviously, trade-offs here. So here we're doing pretty well at 4,000, but as soon as you go to 8,000 and so on, it kind of you run into these problems. Something a little bit more difficult is the number of registers. So that's trickier. So here there's quite a margin of 18, but once I reach 64, that's quite a bit more. But I would again run out of register space. So actually here I'm doing fine with the registers. While controlling the number of registers, this is tricky. By rewriting your code, changing a little bit, the use of local variables and so on. Because essentially the generating code that minimizes number of registers is sort of an NP-hard problem. So the compiler does its best, but it doesn't necessarily find the optimal solution. So sometimes you do the same operation, but you just, for example, introduce new local variables, you change the order of things and so on, and the compiler does things differently and can optimize. Or sometimes you can split a kernel into small kernel and so on to reduce this register pressure. So there are some tricks that can be done, but this is more challenging. Okay, so you can play around with this spreadsheet here. So let's see. Yeah, so now I'm going to have some difficulties getting back my. Where is it? Yeah, it wasn't. Oh, okay. It's in full screen, so it's kind of hidden. Right, it's back. All right. So my slides. So okay. So one thing that this is. I just want to go quickly on that because this is more of a technical thing. How do you figure out the number of registers that is required for running a given kernel? So the compiler can give you this information. So you use a special option. So PTX assembly, verbose, okay? And then basically the output just gives you some information. So for example, this was the transpose, fast transpose kernel, okay, with some C++ compiler, naming stuff, so fast transpose. And then it just tells you, so stack frames, still stores, still loads, and so on. So this is not super, relevant for us right now, but tells you 18 registers, 4,000 bytes of shared memory, and 300 bytes. This is constant memory. And talk about that. It's basically the read-only memory that has a special storage space and is more efficient. Okay? So basically these are two numbers I entered. 18 registers, 4,000 bytes. All right. So this is what you get. Okay. So you can use this spreadsheet to sort of get a sense of what to expect with your kernel, and then you can play a little bit with threads per block. But like I said, as you can see, I mentioned 128 is peak. You have 256 also peak here, 512. So these are sort of 256 or 512 are sort of good numbers because they give you a lot of blocks, and typically you're close to 100% of those. Okay, so in the end, it's sort of often just trial and error, but you can start with 256 or 512 as being good initial guess. Any question on this? Okay. So let's talk about another topic, sort of briefly, but also so very important to understand performance and to sort of understand whether your calculation is suitable for execution on a GPU. This concept of branching and divergent execution paths. Okay. So here there's a special kind of difficulty, which so the basic units are these warps, okay, made of 32 threads. Okay, And every thread in the warp executes the same instruction. Okay, so the hardware is not really tracking the instruction per thread, but it's more at the level of the warp. Okay, and so I'm going to show you exactly what are the consequences of that. So Volta actually turns out is well, for our purpose, it doesn't really change too much, but I'm going to kind of show you what you can do with Volta now. But up to Pascal, which is prior to Volta, and that's the GPU you have on the cloud. Essentially, there is just a single program counter that is shared amongst all 32 threads. So meaning that you're not distinguishing what each thread is doing, rather you're looking at what the warp is doing, and the warp is given an instruction, and that's it. Okay? And the threads are sort of just following the warp, and also all doing the same thing. So let's see what's happening. So now the problem is in your code, there's going to be some branching. Okay, branching could be you have an if, you have a while, or even you have a for loop, but the length of the for loop sort of varies, between threads. Another example of branching. So essentially, it may not be true that all threads actually do, have to do the same thing. Okay, the execution path will depend on your thread ID. Not by a whole lot, but a little bit. I mean, sometimes actually by a lot. I mean, you start having if statements, you really could do very different things. And that's very bad, so you definitely want to avoid that. So let's see what happens. So essentially, here, the GPU or the driver or the operating system of the GPU is going to cheat a little bit. So it really doesn't have this ability to have divergence, right? All threads need to do the same thing, but there is a capability in the hardware to mask certain threads. Okay, so in some sense, some of the threads, they're going to do some operations, but the output is going to be discarded. Okay, so there's ability for to mask certain threads, but essentially everybody still needs to do the same thing. Okay, so aside from this mask applied at the end, everybody's doing the same thing. And so, for example, here, you have an example, if LADX more than 4, so let's just say you have 8 threads in your warp, okay? And so if you're 0, 1, 2, 3, you do AB, otherwise you do XY, okay? So first you start, the first threads are going to do AB. Now the other threads, are not doing anything, or rather they're doing AB, but the mask is being applied so that at the end of the day it's like they're doing nothing. Okay, and then when AB is done, then the code goes to the other branch and does the XY. And then it resumes, every converges, and every does the same thing, okay? So, so you can see how this branching is terrible because now you have a sequential execution of your code, okay? Instead of AB and XY, in principle, those, could be run at the same time because, 0, 1, 2, 3 are doing AB, and then 4 through 7 are doing XY. So those are completely independent, could be done at the same time, but no, it's going to be happening sequentially because of what the hardware is doing. Okay, and this is done through a mask. So the execution is completely serialized, meaning that instead of being parallel, things happen one after the other, sort of sequentially. Okay. So let's look at 2 cases. Okay, just to make the point. So here, for example, something that's called branch thread. So let's look at the code. So what is this code doing? So what are the threads in the warp doing? Right, so basically you have the even threads doing something and the odd threads doing something else. Okay, so that is definitely a terrible case. It's pretty much the case I showed you. So half of the threads are doing the first branch, second half is in waiting, and then when the first half is done, second half does the other part of the branch, and everything is completely serialized. So if you look here, what's the difference here? also even and odd, but done differently.
Everything in a warp.
Right. So now the even odd is at the warp level. Like the even warp are doing this, odd warp are doing that. Okay, so now actually that branching is inconsequential because instructions are kept at the warp level. So, you know, everybody will take the branch, everything goes concurrently, and everything's fine. So of course this example is a bit artificial because in practice it's very hard when you have an if statement to make sure that the branching happens at the warp level. I mean, typically it happens depending on the result of the if statement, which obviously depends on the thread ID, but that's typically uncorrelated with the warp ID. But in some cases you can reorganize the calculation and so on, so that things work out kind of reasonably well. But that's sort of hard to control. But it's very important to see that you have this granularity, and so if essentially threads that are sort of contiguous or near each other take all the same branch, then you will not see the effect of this branching. But if the branching is sort of appears random, if you're uncorrelated, then you will see a massive slowdown in your code. And you have to be very careful because these if statements might be nested and so on, and so very quickly you may have only one thread actually doing anything in the warps. Okay, so that would be terrible. So I want to briefly mention the Volta. This is kind of a recent development. It's kind of interesting, but it doesn't entirely address this. But it kind of illustrates that this branching could really create some serious problems. Okay, so the performance hit is still there. So here is how it's advertised, but it's really not as great as this sounds. So pre-Volta, like I said, the program counter, okay, like the instruction counter, it was at the level of a warp. Okay, so essentially, you have 32 threads in the warp, and then the program counter was right here at the warp level. Everybody does the same thing and so on. So in Volta, they actually have each thread its own program counter. Okay, so actually each thread keeps track of where it is at in the program. Okay. Having said that, the hardware still is such that the 32 cores need to do the same instruction. That is still the same as before. So, what's the difference? Okay, so the difference is as follows, and it sounds like a small point, but I'm going to give you an example showing that, it actually, in some corner cases, can make a big difference. So the difference is, so again, when the warp is running, only one instruction. That is still true, that remains true, so there is a slowdown. But let's look, for example, at this case. You're running, again, AB and XY. So previously, the warp was essentially doing either one branch or the other branch, okay? Because everything was at the warp level. So the warp was the first branch or the second branch. So if you're at the thread level, this is a little bit better. It means that you can have some of the threads, for example, doing A. For example, here you start, okay. First threads do A. But then because the program counter is at the level of the thread, it is possible at the next step to have threads running X. Okay, so the other half of the threads are running X. So now essentially you have inside the warp threads that are actually at different instruction counter. Okay, different places in the program basically, right? They're still sort of executing the same instruction or applying this mask, but in terms of tracking where they are in the program, it's become now independent. Okay, and so for example, then the first threads can then go back to B, and then this guy can do Y and be done, and then everybody actually that's wrong. Okay, here everybody should be doing Z. That's one error in the, so here basically there's convergence that everybody goes back and does Z here. So actually this was done in part because there are several bugs that can come from this fact that a warp is stuck at a certain instruction. Okay, several bugs that can appear in programs, and so I'm going to show you one example of these bugs and just move on. So this is kind of an interesting, so again, this is more going a little bit beyond this class, going back to some of the core topics of parallel computing. And so we talked about mutexes and so on, for example, and locks. So essentially, you have situations where you need to access a shared resource and using locks. Okay, so this is the example I'm going to take. The threads need to access a shared resource, so they need to use a lock to access that resource. Okay, make sure that no other threads can do that at the same time. Okay, so you have so-called starvation-free algorithms, which are basically algorithms such that even when you have a contingent resource like a lock, you're still guaranteed to complete. Okay, just to sort of simplify the discussion here. So now let's look at this code. And if you look at this code, it doesn't seem very problematic. It's just a linked list, okay? And you're using lock to, I'm going to skip the details of the algorithm, but this is just a linked list. And you're inserting a node in your linked list. And so before insertion, you have to do a lock. Okay, so you lock your nodes, you make the changes, you add this B, and then you just unlock everybody. So this is, we've seen code similar to this. Okay. And what is the problem with this code? Actually, there's a very subtle problem in this code because of the lock. Can anybody explain what the problem could be here? So it's not very easy to spot, actually.
So if you have a thread that's trying to access the node before it.
I'm sorry, what?
If you have a thread that's trying to is accessing the node before A.
No, so it has to do, the answer has to do with a deadlock situation. So it's actually tricky because it's to see the problem you sort of need to, it depends on how lock is implemented. Okay, so it's not actually entirely visible. But when you enter a lock, there's definitely an if statement. Because one thread is going to continue and others need to stop. So now you have to look at exactly what's going on with this lock. But let's say that, for example, one of the threads, acquires the lock. But let's say the warp decides to look at the instruction, which is, so basically looks at the thread that could not acquire the lock. Okay, so the instruction for the remaining thread is to just test the lock. Okay, so the warp is going to say test the lock. But the problem is, unless the warp starts executing the thread that owns the lock, you're going to be stuck, right? Because the thread that owns the lock is not going to make any progress. Okay, so here you need to actually do a divergence, right? The thread that owns the lock needs to be able to move forward, right, while the other threads are waiting. So it's kind of a weird problem, okay? Mind you, if the warp decides to go with the thread that owns the lock, actually you're fine. Okay, then everything would execute. At some point it would unlock, would go back, and so on. But if the warp at some point decides to stick with the threads that are testing the lock, then you cannot make progress. Okay, so probably took a while to figure out that bug. Because somebody probably took some code that they had and wanted to run it on a GPU, and this would completely randomly, a deadlock, and this is the type of bug that's very, very hard to figure out. And so curiously, Volta, by allowing threads to make progress with their own program counter, can actually get around this type of problems. So I think this is a kind of interesting example of the sort of difficulties you can have in multi-core computing, and specifically because of this lock, of this warp, and the fact that all threads are executing the same instruction, and how this change in Volta sort of gets around that. Okay, so let's talk about the homework now. So this wraps up. So again, next week we're going to have the CUDA lectures. And then just a couple of lectures to basically, after that we're sort of done more or less with CUDA, and then we're going to be moving on to NPI. So homework 4 is a little tricky, so I want to talk about a little bit about it. So the homework itself, there are some difficulties in the programming and so on. I mean, nothing you know, like theoretically mind-boggling, but it's mostly about figuring out out-of-bounds problem, like looking at indexes and, you know, checking whether you're inside the domain or outside. So nothing like really earth-shattering, but you know, sometimes it takes a while to kind of figure out how this indexing kind of works out. So the idea is to, you know, do a fine difference. So this is a classical, just benchmark or demo, you know, with CUDA. So you have fine difference scheme. So I'm going to skip the how this works, but you know, so you have a so Euler method, explicit, and so essentially there's going to be some linear operator like a sparse matrix or stencil that you apply to your temperature at time n, and gives you the temperature at time n plus 1. Okay, and you know, involves the time step, involves the discretization of the second order derivative with fine difference and so on. So, but the detail of the math don't matter. This is just a sparse operation on Tn. And so this can be represented as a stencil. So what it's showing is the red node in the center is the node being updated, okay? And around are the dependencies. So we're just going to look at the 2D grid for simplicity. So the node at location ij is going to need the node west, east, north, and south for its update. Okay, so it's the second order. Fourth order, you need to go to more neighbors. So basically these are you know, approximations of your second order derivatives with different orders. So you have the central difference, second order. If you go to more neighbors, you get higher order schemes that, you know, the error decays more rapidly with the mesh size. Okay, either h squared, h to the 4, or h8. Okay, so h8 you have to go really, really far. What's interesting is depending on the nature of the numerics, the stencil you're using, you can get different performance in your code, right? The number of gigaflops actually is going to change, okay? So obviously here, you have more flops, but what I'm talking about is the performance, like the number of flops you're doing per second. Okay, so here you're going to be more flop per second, going to go faster, going to be more efficient than with the second order, okay? So the efficiency is going to be different. So you're going to have to kind of think about that. So there are various details in the code. I'm skipping through a lot of that, just in the interest of time. Just to note that, for example, you know, there's a little problem with the boundary, okay? Because if you have a fourth order stencil, you need two neighbors, you know, west, east, north, south, okay? So on the boundary, you know, in principle, you know, there's nobody, for example, let's say you're on the left boundary, there is nobody, you know, left of you. So you need a special stencil, but, you know, we sort of here ignored a little bit these details because they're kind of tedious and not really relevant for our discussion. So the way we did that is essentially, you know, you're running a case where we have essentially an eigenmode or eigenvector of your PDE. So it's just a decaying mode, okay? And so, you know, we have the analytical solution, so we can essentially set the values on the boundary sort of analytically, so we don't have to worry about that. So the point is, nodes on the boundary are set by a special routine, and just have to worry about doing the calculation inside. Okay, so basically we're just going to apply the same stencil for all points inside the domain. Okay, and we're done with that. Okay, so implement a CUDA routine to update the nodes inside the domain with a fine different centered stencil. Okay, so just a little bit about the how things are laid out. So you have a 2D mesh, okay? You need to decide, you know, so in memory, of course, everything is just 1D, so to speak, okay? There's addressing and so on, so you can think of it as 1D. So you need to decide how you're going to map this 2D domain onto, you know, this 1D sort of memory. And so the way we do this is we move first along X, okay? And once we're done with this row, we move on next row and append and so on. Okay, it's called lexicographical order. So now here's the key diagram. Okay, here's the key diagram, and so this is a very important diagram to think about when writing GPU codes. This is something I mentioned a couple of times already. And so it has to do with this concept of arithmetic intensity, which is the number of flops per byte that you need to do. So what this is saying is if you're doing few flops per byte, okay, not too many flops, then you're limited by the memory bandwidth. So in fact, in your homework, for example, right now, when you're doing the int or the int2, okay, you're doing relatively few flops per byte. Okay, you have this load store instruction, but then they request a lot of data. So few flops, if you divide flops per byte, it's a small number. So you're going to be on the left, you're going to be memory bound. So actually in your homework, you know, because you're doing this memory copy, you want to be memory bound, but you know, in most cases, you're trying to do some calculation, and you want to be flop bound. Right? You want to be limited by your memory. So being on the left here is typically not that good. Okay, and if you're able to reduce the memory traffic, so again, going back to your homework, you know, in the case of car, you're actually loading a lot fewer bytes from memory, but pretty much doing the same flops. Okay, so actually your compute bound, which was bad. But for example, again, if you're processing this grid, what you're interested in is in applying the stencil, so doing these multiplications, additions, and so on. So you want to do the compute at peak bandwidth, so you want to be on the right here. And so that means, you know, high arithmetic intensity, and it's quite bad. You can see that here this is a 10, but this is flops per byte. So for example, say you do a float in 4 bytes. So it's more like flops per 4 byte that you need. So essentially, you need to multiply by 4. So this number, you know, corresponds to more like 40 flops per float. So 40 flops is a lot, right? That is a lot of multiplication addition with just a single number. So arguably, you know, you're going to load a bunch of numbers, but you know, that's per number read from memory. That is a lot of operations. Okay, and you know, if you want to get to peak performance, you know, maybe you need to be even more than that. Okay. So this is a key thing to understand. You know, how many flops are you doing per word read from memory? Okay. So so you know, these are, for example, what's happening with sparse matrix multiplications. So you have very few flops. You're right here. Dense matrix multiplication. So here you're going to be reaching the maximum throughput, and also this is differentiating GPU and CPU. That's you know, with sort of different performance, but this is just showing some example. So also, you know, related to this, you know, so to understand, you know, this issue of performance, you need to understand, of course, the memory traffic. So if you want to see if the bottleneck is compute or the bottleneck is memory, you know, you need to understand how fast your memory is. And how fast your memory is depends on where you're reading data from. Okay, if you're reading from L1, it's extremely fast. L2 slower, very, very slow. Okay, and the size of the cache will determine, you know, whether your data, you know, is still in L1 or maybe it was evicted, so you have to go to L2. It was evicted to go to L3 and so on. So this is what things look like on NVIDIA. So it's actually skewed very differently. You have a ton of registers because, you know, all these threads that need to be live on the processor. You have a ton of registers, whereas the L2 cache and so on per thread is actually sort of very small. Okay, so you're going to be very constrained. So it's very hard to use cache actually on GPUs. So, but this is important because, you know, if you're reading from L2 or from main memory, the bandwidth will be very, very different, right? So for example, if you're reading from L2, then your arithmetic intensity can be way lower, right? Because the memory will be like super fast. Okay, so you know, you'll be able to be compute limited even at a lower arithmetic intensity. But if you really need to go from main memory constantly, then you need to bump up the arithmetic intensity a lot. Okay, so now there are a couple of calculations you can do. So, so on this simple example, you can actually completely figure out where you are on this diagram. The more complicated code, you know, it's way more difficult. But you know, when you look at your code, you can count how many flops you're doing and how many pieces of data you're reading. So you can actually, you know, do this type of calculations. So let's take an example here. So here is, you know, what the second order stencil looks like. So you can just count. Okay, this is 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so you have 10 floating point operations. Okay, and then you can just read, well, how much data you're reading. So you're reading this guy, this guy, this guy. So basically 5. Okay, so you're reading 5 numbers, and you're writing 1 number. Okay, so current 0 is actually being read, and then you have to write the results back to memory. So it's more or less 6 numbers. Okay. So you can just count all that stuff. So 10 additions, multiplications, read, write, total is 6. Okay, and then you can calculate your arithmetic intensity and try to improve that. So let's see how this is going to be done. So there's going to be 2 main ideas in this homework. Okay, the first one is going to be the use of cache, shared memory. So essentially, this idea is you're going to load data into the cache and try to reuse it as much as possible in order to reduce memory traffic. Okay, so you keep it there and do as many flops as you can with it before writing back the result. And the second, which is a little bit easier to figure out, is that the memory access should be coalesced. So let's go through. So there are 3 essentially implementations, and depending on the algorithm, you're going to get different arithmetic intensity, and it's going to be better and better across the 3 algorithms. So the first idea is the easiest, where essentially a thread block simply reads, the memory just contiguously. Okay, you just go through memory contiguously, so basically sort of reading row by row in your grid. Okay, so your thread block is going to, thread 0 works on this, thread 1, 2, 3, 4. So essentially, thread 0 is going to start reading this, reading this, reading this, reading this, reading this, doing the flops, and then writing the result. So it's okay. It's not that great, but there is. For example, if you take this point here, it's actually being used by 3 threads, right? That thread and then the guy on the left and right are both using that guy. Okay, so there's some reuse. If you look at the top and the bottom, okay, no reuse. Only 1 thread is reusing that. Yeah.
When the threads are simultaneously reading and writing, is there a race condition that we need to avoid?
Well, okay, so they're not reading and writing to the same memory location, right? So for example, you have 2 arrays in this thing, right? There's Tn and Tn plus 1, right? Yeah, because otherwise there would be a race condition. Yeah, that's right. Yeah, on a CPU, you can work your way around that, do it in place, but here it's more or less impossible. Yeah. Okay, so for example, here, let's say you have 16 threads. So you look at all the reads, okay, so it's basically 16 times 3 is basically those 3 rows, okay, and then you look at all the flops. So there's a little bit of reuse, so the flops per word is 2.4, okay, because the guys in the center will basically have 3, but then the boundary is, just used by only 1 thread, so, 2.4. So you still, so in the end, we're not going to be able to be compute bound, because it's just, sparse basic operation, not possible to be compute bound, but the idea is still to reduce the memory traffic. So actually it doesn't matter what flops you're doing here, we're going to try to rearrange the calculation so that, we make better use of the cache, and we can reuse data. So the second idea is going to be as follows, okay? That if you read a square, it's actually much better. Because if you think about it, right, if you have, for example, a node here, okay, let's say second order stencil, at most it's used by 5 threads, okay? So whenever you have a node that's inside, it's used by 5 threads. This guy here is used by 4, and this guy here maybe by 3. Okay, so the more you're close to the boundary, the fewer threads are sort of accessing your data. So it's good to be inside, and less good to be on the outside. And in the 1D case, that was sort of the worst. Okay, you had the smallest reuse. And again, you know, the stuff on the boundary here is used by only one thread. Okay, so that's yeah, it's hard to avoid. So okay, so you see that roughly speaking, the maximum is achieved when the volume divided by the surface is maximum. Okay, or maybe an easier way, you know, if you've done some mechanics, an easier way to think about this is surface divided by the volume is minimal. So this reminds you of what problem? For those of you who've done fluid mechanics.
Droplet is spherical.
What's that?
Water droplet is spherical.
Right. And do you remember why is that?
Surface tension.
Right. Yeah. Exactly. Okay. So good training in fluid mechanics. So you have this concept of surface tension. This concept that when you have an interface, essentially between water and air, there is some energy cost, which is basically has to do with you could say cutting hydrogen bonds, more or less, right? Instead of having water molecule with nice hydrogen bonds all around, it has much fewer bonds, so there's this energy cost associated with the surface. So you want to minimize the surface. So for example, in space, okay, you have all these jokes, you know, Tintin, right? When Captain Haddock drinks his whiskey in space, it's this perfect sphere. It's difficult to drink his whiskey. Okay, so in space, when there is no gravity and so on, you know, the water just you know, goes into this nice bubble. So here, you know, would be a disk. Very difficult to do, but you know, a square is a closest. So the square is the one that achieves the optimum, and in fact, the bigger the square, the better. Okay, the ratio just so in fact, if you have a very big square, everybody's in the inside, and you reach the peak arithmetic intensity. Okay, so so for example, if you do this, then you reach, you know, you go from 2.4 flops per word to 3.3, and you can do a little bit. So I'm going to skip here, but you can do some calculation showing you that the maximum is actually 5. Okay, so I'll let you, you know, now look at the details in the homework and so on. So there is a so-called global memory implementation where you have a thread block, so no shared memory, just basically still accessing global memory and so on. But you're going to have a thread block working on a square on your mesh, and essentially you're going to have a bunch of warps, you know, reading a bunch of rows, and then moving on to next rows and so on. Okay. So the reason is, if you take a square is actually too big. That's too many threads. Okay. In your thread block, you know, if your thread is 256 or 512, you actually cannot, you know, allocate the thread block, which is as big as the square. I mean, the square here is going to be 32, right? So 32 by 32 is too big. So instead, you know, you can have your thread block working on a couple of rows, and then the threads are looping so that you can cover the entire square. Okay, so you're going to loop. You have a loop along Y, so that you start with a couple of rows, and then you can do the process the entire square. Okay, so here when you write this code, you know, looks the same, but the idea is that, for example, let's say you have just 2 warps working. So first, the 2 warps load. Okay, so they're going to be loading this, and so on and so forth. Okay, then you're done. Now, when you move to the next stage, okay, one of the warp is going to work on this, but this is already in cache. This is already in cache. Okay, this is going to be loaded, so you're going to be able to reuse a lot of stuff that is sort of at this interface between the warps. Okay, and this is how you can get good usage of reduction in the memory traffic. This overlap. Okay. But it's sort of invisible because you're just using the fact that it's in cache. Okay, so you need to think about where the data is and realize that at this point, you know, some of the data is in cache. Well, you know, there is obviously some data that needs to be read from global memory, but whatever is in cache is going to be very fast. So this reduces the memory access. So this is going to be the second algorithm. Okay, and okay. So now the next thing is this. So the second point is a little easier to see, is this issue of coalesced memory access, or accessing nice chunks of size 32 bytes, which are actually just 8 floats, but you can try to go for the full warp working. So actually, we didn't. I don't think I tried. Yeah, so the size along x is going to be a multiple of 32, but now I realize that you could actually, since the cache line on the Kepler is actually just 32 bytes, which is just 8 floats, you could actually try, a smaller, a shorter chunk size along x. But the idea is you need to be coalesced, okay? So what this is saying is, since it's contiguous in memory, this coalesced access, or this cache line, is going to set this dimension here, okay? So there's going to be some issue of offsetting, okay, because, things do not start exactly at the right address. But you want this length here to be, a multiple of, say, 8 or 32, so you have this nice memory access, okay? So this is going to essentially fix the dimension of your, along x, so you want to, have multiple of this. And then once you're happy with your x dimension, then you're going to decide on your y dimension. So the y dimension determines the number of threads per block you have. Okay, and that's going to be this 256, 512. So here, this is kind of, limited or set. So this is going to determine, how many of these rows you have. Okay, and now that is a thread block. And now remember, you want to do a square. So you're going to again iterate, across the y-axis to do your square. Okay, so this is going to explain here. So along x dimension is roughly 32, although you could try 8, but you want a big block, so 32 is probably a good bet here, but in principle, any multiple of 8 might work, so there might be some wiggle room. I don't think we tested that, but maybe you can investigate this a little bit. But then along y, number of warps along y, this will determine the number of threads in your block. So, let's say you want 5, 12 threads, x is 32, so actually this is 16. Okay, but if your square is 32 by 32, then you need to iterate just twice. Okay, and then you have your entire square done with that. Okay. Okay, so here just to note that you can have some issues with the bounds, so you have to be very, very careful, because now each thread block is just working on a small chunk of the grid. So you've got to tile all your thread blocks correctly, and then you have just integer blocks. So some of the threads will have indices that go beyond the end of the grid. So there's going to be some if statements. This happens along x, this happens along y. So there's just a bunch of if statements here. You have to be careful with that. Okay, and then finally, shared memory algorithm. So this one is, so basically what you're trying to do here is, because this algorithm is simple, we've completely determined the memory access. Okay, we're reading, doing these calculations, writing. So the cache does a pretty good job, but the problem is the cache is kind of small. And you have, it's just L2. And so all the thread blocks are sort of competing for that space. Okay? And so if a warp, for example, you can have, a bunch of warps reading some data here, okay, and then they have to move on. But in between, it's very possible that the data has been evicted from the cache, in which case, this whole scheme sort of falls apart a little bit. So if you want to make sure that the data that you read is here, then you have to use shared memory. So also, shared memory is L1. And so, it also gives you access to this very fast space that otherwise, it's more or less not accessible. Otherwise, it's just L2 and so on. So to access L1, it's, reasonably big. It's very, very fast. So that's something you want to do. So the way things are going to be done is first, you're going to load in shared memory. So again, remember that there's a little bit of the stuff on the border because the stencil, extends a little bit. Okay. So second order, fourth order, eighth order stencil. So the way to write the code is because you're limited by memory, you want to basically focus on the reading. Okay, so you're going to decide on your thread block based on reading. So your thread block is going to read this entire square. Okay, so first step is all threads just read, and then there's async threads. Okay, after that next stage, then you have a compute stage, where essentially threads that are sort of inside do the calculation and are responsible for updating here. So it's going to be an if statement, because basically other blocks will do this update here. This block is only responsible for these guys. Okay, so there's going to be a little bit of if statement here. But again, the compute is very fast, so the fact that some of the threads are idle is going to be relevant here. Okay? You have to focus on the memory bandwidth and the read and write. Okay, so basically that's more or less it. So this is sample output. You can come back to that. I just run this morning. These are what the numbers I'm getting. So you can see how you have global, which is three algorithms I talked about. You can see how the runtime goes down. The error. So between CPU and GPU, things are done in different orders. So although everybody supports the IEEE norm, the ordering, the operations are non-commutative. So you get this round of errors. Yeah.
On the slide before this,
Yep.
So you said that the perimeter area will get covered by some other block.
Right.
So does that mean that inside the red block, like the data along the bottom, basically it's going to get loaded twice. It's going to get loaded once by this block, and then the other block's going to also load it.
Right. Yeah. Exactly. Yeah. The stuff on the boundary gets loaded by multiple blocks. So that stuff might be in the cache, but in terms of shared memory, it's going to be duplicated in shared memory essentially. There is no avoiding that. Actually, technically speaking, the stuff on the boundary is only used by one thread. So you could load it in register. That's a little optimization here to save shared memory. Because the stuff on the boundary technically is not used by any other threads. Only the stuff in the middle is actually shared, truly shared. But that's a small, that's not implemented in the solution set. It's kind of complicated. That's a small. So here you have two different orders. Eighth order, I should give you highest bandwidth, gigabyte per second. You go up to 800 gigabyte per second. I want you to remember the peak. Oh well, but that's not the. That just sounded too good. I think these numbers are too high, but because this is not the true peak, it's just basically because part of it is in the cache essentially, so it's way higher. But it's basically based on the runtime, and in some sense the data you're reading and writing, but theoretically, assuming there's no cache, that's why you get this very high number. But anyway, you get 800, and so here you get lower numbers because it's order 2. So essentially there is way less reuse here. Right, so you're much less efficient. Okay, and I think this is just the last slide. So now you can think of what's the best possible algorithm. And the best, so here it gets a little tricky, but essentially, if you want to push these ideas, you want to create the biggest square possible. Okay, so you can iterate along the y-axis. Okay, but so the idea is you want to create the biggest square. So essentially, you're going to allocate as much as you can in this x direction until essentially you run out of shared memory. Okay, you're going to load then just a couple of rows here. Okay, and then you need to figure out some complex like pointer arithmetic and so on. So that essentially you start computing here. Then you load the next block in shared memory, and this is the part that sort of overlaps, and you do your update, and then you go on like this, and you traverse as far as Actually, going up, you can go as far as you want at this point, okay? Because you're constantly sort of reusing data in your shared memory as best as you can. There is interesting also optimization, which is that the grid may not be that big. So there's always a trade-off between how big your square is, which is good for arithmetic intensity, but then if you take these gigantic squares, you have relatively few blocks that are running, which is not good for concurrency. So there's a little bit, for small grids, there's a little bit of trade-off between small squares that are inefficient, but you have more of them, and very big squares that are very efficient, but then you have fewer of them, and so not too many blocks running. Okay, so this wraps up homework 4. And so we'll get the guest lectures on Wednesday then. Okay, thank you.